So welcome again. Last week, which is our third week of facilitation, we discussed Cauchy sequence and some other topics that we left over in the second week of the facilitation. So I think is it Amos or somebody that asked me a question that has to do with an example about what we meant by saying Cauchy sequence is convergent. So I've tried to find some example which we can quickly go over before we move to what we are supposed to discuss for the fourth week of facilitation. So I said Cauchy sequences are convergent. So the theorem is that every convergent sequence is a Cauchy. So the question now is that how do you know that a sequence is convergent or a sequence is converge at a point? So now the proof is that let's assume that we have A, which is an element of a set R. Amos, please, you can mute your mic, please.
Okay, sir.
Okay. So now let's say that we have A, which is an element of a set R that tends to L such that epsilon is greater than 0. So now, if you now consider that there exists an N, like I told you last week, that it's just like a building. In a building, there are different rooms. So the building in this case serves as the set, and the rooms inside this building are the elements of the set. So in this case now, we have N, which is like a building. So if A, which is a subset now, belongs to that N, so we can say that K, that is an arbitrary value, which is greater than or equals to N, must tend to the modulus of AK, that is, if you count K, maybe K1, 1, K2, K3, K4, K5, up to K, then minus L, the result must less than epsilon divided by 2. So if Mn is now greater than or equals to N, we have the modulus of Am minus L, which is less than this, and modulus of An minus L, which is less than this. So by the time you combine them together using this concept, we now see that the modulus of the difference between Am and An must be less than or equals to the modulus of the entity, that is Am minus L plus An minus L. And we have defined that Am minus L is epsilon over 2. By the time you hide them together, it will give you epsilon. Is that taken? So at this point now, this function has converged to epsilon E. So this satisfies the condition that Cauchy sequences are always a convergent sequence. Is that taken? It may look abstract because you are not a mathematician, but you just need to take time to understand these procedures. So at the end of the class, I will send the PDF file of this to you so that you can go through it again. So having said that, you have a question? Yes. Somebody wants to ask a question? Okay, fine.
Go on, sir.
Okay, having said that, so we move to today's lectures, which is basically centered on geometric interpretation of complex function. So I didn't prepare any slide for that because I sent a note to you earlier on in the first week of the lecture. So you should have the notes by now. So I'm going to use that note for the lecture. So which is this. I think you can see it, Abi. So geometric interpretation of a complex function. In this case now, just be attentive. I will try as much as possible to be able to simplify this aspect so that you can grab the concept. Once you grab the concept, to solve problem here will not be difficult. So what we're trying to say is that, you know, when we started discussing complex number, we started by trying to express complex number in terms of real and imaginary. And we defined that in the real part, you have x, while in the imaginary part, we have what? Y. Now, by the time we move to a complex function now, we have introduce another concept into it, meaning that you have an equations in which you have two variables. So each of these variables now, we can classify them or group them into real and imaginary. In doing that, if in doing that, we say that if you have a D that is a domain now of a real function such that u of xy and v of xy satisfy this equation. So in this case, our u is u of xy and our v is v of xy. So if you try to put them together, that is moving from one plane to another, we want to do a kind of a transformation now from a d plane to an xy plane, because if you look at this now, there are two variables, x and y. So combining these two variables together now, we can actually use them coupled with the complex function that we defined 2 weeks ago to define an expression that we can use to solve problem in geometrical interpretation. So now, what we are going to arrive at is that if you move, from D in XY plane to another plane called UV now. So this UV plane is known as W plane in complex function. So this W plane now, we can express it as f of z. So z here now is a complex number. So now trying to now express z now in terms of x plus iy, it will now be u of xy. So u in this case now is representing our x in the normal complex number analysis, while v of xy here is representing our y. Is that taken? So you now see that we have an imaginary value high. So f of x can now be written as u x plus y plus iv of xy. So this is just like transforming from an xy plane to a w plane, and also writing a d in z plane onto a range in w plane. So if you try to look at an example now, you understand this better. So let's look at this example. So in the note that I sent to you, something is missing here. So I'll be telling you now, so you write it down. Are you with me? So we are supposed to have f of z is equals to u x comma y plus iv x comma y. Is that taken? So now, if you have that, we know that in complex number, z is equals to x plus iy. And we also know that we can find the complex conjugate of z. So if you now say that our f of z now is equals to this expression, is equals to this first expression, this is our f of z is equal to this expression. So what you are expected to do is that to rewrite this expression in terms of this function, f of z is equals to us comma y plus iv x comma y. So the simplest thing to do is just to collect the like terms. What do I mean by like terms? Now, if you look at this term, there are about 5 terms here. 1, 2, 3, 4, 5. So you see that out of these 5, 3 of them does not contain I, which is imaginary. So those that only contain I, you bring them together, which are x to the power of 4 minus 6x squared, y squared, then plus y to the power of 4. You bring them together, then plus those that has imaginary in the inside the expression, you bring them together as well. So the first one there is 4i x to the power of 4 y, and the last one is 4i xy cubed. So by the time you bring them together, you have I into the bracket of 4x to the power of 4y minus 4xy to the power of 3. So you can see that we have rearranged the expression in a such a way that we have grouped them to those that has imaginary sign and those that doesn't have. Those that doesn't have are typically the real part of the function, and those that has are the imaginary part of the function. So by the time we rewrite this now, you now see that our u of xy is just this expression, x to the power of 4 minus 6x squared y squared plus y4. So and v of x is 4x to the power of 4 y minus 4x y cubed. Is it clear? Is it clear?
Very clear, sir. Yes, sir.
Very clear. Good. Amos, do you understand that?
Yeah, yes, sir. Yes, sir.
Okay, good.
I understand, sir.
Now let's proceed. Let's look at the second problem there now. This is the second problem, example 2 now. You are have to express the function f of z is equals to the modulus or the conjugate of z, then the real part of z plus z squared plus imaginary of z in the form of f of z in this form. So you have to rewrite this expression, this whole expression in this form, like what we just did now, in this form. So now if you look at this now, something is given to you, but the information is silent. And what is that, Amos? In the expression, something is given to us, but that thing, the information about that thing is silent. Amos or anybody, what is, something is given to us, but that thing is silent in the questions. What is that? What?
Z.
Z, good. And Z is equals to what?
Okay.
Z is equal to what from our
Okay.
from our complex number?
X, I, Y.
Good. Z is equal to X plus IY. So now the RE of Z is what now?
Then
the real part of Z is what? I gave you all this in our second class now.
X.
X, good. Now, if you now find the conjugate of Z now, what would that be? If you find the conjugate
X
of
minus
Z now,
IY.
it will be what?
X minus IY.
Good. So now we have, what is now the imaginary part of Z now? The imaginary part of Y. Good. So now by the time you now put all this information together now, you will arrive at this expression that f of Z is equals to this X minus IY into X. So this is the modulus of, that is the conjugate of Z multiplied by the real part of Z, then plus the square of X of Z, then plus the imaginary part of Z. By the time you expand it, you have it in terms of those that have imaginary information in them and those that doesn't have it. So you group them into two now. So the whole of this now is now your US, Y, and the whole of this is your VS, Y. Is it clear? Is it clear?
Yes, sir. Yes, sir.
Okay, good. So I think there are about 2, 3, 4 questions there again, which you need to look at yourself and try to solve to understand the procedure. Another concept that you need to understand here is that in some problem, you may be asked to rewrite the expressions in terms of Z or in terms of Z and the conjugate of Z. So what you need to put in mind is that X can be expressed as S is equals to Z plus the conjugate of Z divided by 2. And Y can be written as Z minus the conjugate of Z over 2I. So these two terms is what you need to solve such problem. Let's look at this now. Example 3, it says express f of Z is equals to 4x squared plus I4y squared by a formula involving the variable Z and Z bar, which is the conjugate of Z. So now, what you just need to do is, where you see X, you substitute that with X plus Z, Z plus Z bar divided by 2. And where you see Y, you put Z minus Z bar divided by 2I. So now, you have 4x squared, you put this, you have Y, you put them, then you expand it. By the time you do the expansion, you have something like this. And that eventually will give you f of Z in terms of Z and Z bar. Is that clear? Is it clear?
Yeah, I'm trying to refollow it, sir.
Okay. Just look at it. It's just straightforward.
Okay,
where you see X, you put this because S is equal to Z plus Z bar over 2. And where you see Y, you put this because Y is Z minus Z bar over 2I.
Okay.
Is it clear now?
Yes. Yes.
So you just expand, just like algebra, just expand it and
Um,
you have a kind of a linear equation in of order 1 or order 2 or order 3, depending on the nature of the polynomial that you are going to arrive at. Is that clear now?
Yes, sir. Got
Good.
it, sir.
So now, there is this example 4. Last week, I tried to introduce polar coordinates. I think you remember. I introduced a polar coordinate that has to take into consideration epsilon I theta. You remember very well. So the way we solve for a linear equation or a linear complex number, we can as well do the same thing for a polar form. So if you look at this problem now, example 4, say express f of z is equal to z to the power of 5 plus 4z squared minus 6 in a polar form. Now, last week, I told you that z in a polar form is equal to what? Oh yeah, now. Z last week.
REI
R,
RE raised to power I theta.
good. Z is equal to R exponential I theta. So if you are not trying to rewrite this expression in a polar form, where you see Z, you just put that value, R exponential I theta, then you expand. The result is going to be in a polar form. So if you look at this now, f of z, so we put R exponential I theta, z to the power of 5, we put z there, then to the power of 5, z to the power of 2, then we expand. By the time you do the expansion, you have something like this. Then you now group them again. You group them to those that has imaginary sign and those that doesn't have. So by the time you do that, you have them in, instead of xy now, the two variable here is now r and theta, the radius and the angle, the argand angle, which is r and theta, which is in line with what we have discussed some minutes ago. Some minutes ago we only consider uxy and vxy, but in this case, the variable here is r and theta. It should now be r theta and r theta. Is that clear?
Question, sir.
Yeah, go ahead.
Please, can you give an example of one of the expansion, just to be clear in this?
Now, look at this expansion now. If you want to expand this now, r to the power of r exponential I theta, if you want to expand this now, this means that you multiply this in 5 places. Is that taken? And if you want to do that, straightforward, 5 will just come to the power of r, it will be r to the power of 5. Then 5 will come onto exponential I theta. And if this happen, you know I gave you an expression last week. So you need that to be able to solve the problem. I will show you the expression now. Just a moment. You remember this expression? John, you have a question.
Yes, sir.
So where you see exponential I theta,
Yes, sir. I remember.
So this is what they use in solving the problem here. So where you see exponential I theta, you just replace it with cos theta plus I sin theta. That's what happened here. This one, they just replace it with cos theta plus I sin theta. And at this point now, you need trigonometric function. This is where your trig skill needs to come into place. You know, there are a lot of functions in trig that will give you, that is what they have used in solving the problem here. So once you substitute exponential I theta to equals to cos theta plus I sin theta, you have some expression which you cannot relate to trig function. That is what you are seeing here. And I know that is what is giving you issue, John. So you just need to go and look at some trig function. You know, there are a lot of trig functions that are very simple to master. You have one that say that cos square theta plus sin square theta is equals to 1. And you have one that say that sine plus sine into a plus b can be written as sine a cos b plus cos a sine b. These are expressions you need to look at and see how you can use them to simplify this type of expression. You can try it yourself. If you don't get it, by next class, I will help you to simplify it further. Is that taken? Is that taken? Are we together?
Yes, sir. We are
Yes, sir.
together, sir.
Okay, you can try it. It is just trig function. Once you substitute exponential I theta is equal to cos theta plus I sin theta, you are already in trig. So you just need to be bringing in trig identity to be able to simplify things further. Just try it. If you cannot get it, next week I will solve it for you. I will simplify all these things for you. They are straightforward things. It's just identity that you need to substitute and break things down. Is that taken? So the same thing happened in example 5. So you have to try to look at all these examples at your own convenient time and understand the procedures needed in solving them. So in conclusion of the class for today, you see that example 1 and 2 above have shown how to find u of xy and v of xy when a rule for computing f is given. Conversely, if uxy and vxy are two real value functions of the real variable x and y, we can also determine a complex function f of z in this way. And I told you some minutes ago that your s can be written in this form and y in this form, which allow us to transform from x to z. Is that taken? So there are some questions here which I expect you to try and solve based on what we have discussed. They are straightforward things. Are you getting me now? So any question? Amos?
Sir,
You have question?
no, sir, but I will try to reach you, sir. I will try doing this TMA.
Okay, better. Just try it.
Yeah.
If you have issue,
Yes.
get across to me by mail. I will respond to you.
No
But sir,
problem,
we
sir.
did not deal with Cauchy-Riemann equation.
Cauchy-Riemann equation.
Equation.
It's just,
We did not
it's an
discuss it.
expression. I will tell you that next week.
Okay.
I get me now.
Okay.
I want you to first master this concept first. If you master this concept and you are able to discuss them on your own and use them to solve problems, then by the time I gave you an expression that discuss Cauchy-Riemann equations, you will not mix them up. Is that taken? If you
Yes,
watch
sir.
very
Yes,
well,
sir.
my style of teaching is just to keep a topic for the next class so that we can use that to enter the next topic. If you have been following that.
Okay, sir. Yes, sir. Would we also discuss entire function?
What?
Would we also discuss entire functions?
So these ones, they are just conversion of complex number into trigonometric function. They are straightforward. This one now, let me tell you this. This cos z is just like
Yes,
writing
sir.
cos theta is equals to exponential I theta plus exponential I theta divided by 2. The same thing, sine also has its own. Cos also has its own. Sine also has its own. They are identities. You can search them on Google. If you put
Okay,
it on
okay,
Google now, you get those things. They are identity, standard functions.
okay,
That taking,
okay, sir.
it's not something
Yes, sir.
difficult or how do I put it now? Something that is coming from somewhere. They are identity in mathematics. Is that taking?
Yes, sir.
Yes, sir.
Okay, good. So any other questions? If you don't have questions again, I think we have to stop the class for today. Then we'll meet next week. So thanks for coming.
Okay, sir.